My name is David McComb. I'm a mechanical engineer working for Blacoh Fluid Controls. Question that often arises is how to correctly size a dampener and kind of predict what kind of pressure fluctuations you're going to have in a system. Normally we're talking about positive displacement pumps. They put out a little pulse into the piping system, and that creates a pressure fluctuation, which is often what we want to get rid of. So anyway, we're going to talk about that. We're going to talk about different pumps. We're going to look at a bunch of different pump pressure over time curves. We're going to look at some formulas, and then we're going to kind of go over some other factors that we need to look at, and the conclusion. All right, so let's get into it. All right, here we have a triplex pump, which is generally considered to have a very smooth output, which it does compared to other positive displacement pumps. And that, of course, is because you've got 3 pistons, and when one is giving an output, another one, there's overlap. So you've got one piston putting out, and when it finishes, the other one has already started. So it makes a fairly smooth flow. If you look at a theoretical graph of what the 3 pistons will do, you have one piston starting to put out flow, and then it kind of peaks and then finishes. But the next piston starts kind of on the downward stroke here. So you have this overlap. So you actually get 6 pulses for a 3-piston pump. But they're not super huge for the pump size. So that's a theoretical curve. Here's a actual curve. You can, if you look closely, you can pick out the pistons. So you've got a valley here and a valley here, and then there's like 3 peaks there from the 3 pistons. And then you've got the little peaks there as well. 6 pulses per cycle, per 1 revolution. The blue line is with a dampener in place. You can see it takes out the spikes. All right, let's look at another one. This is a pressure curve from an air-operated diaphragm pump, or a double diaphragm pump. It would be quite a bit different than that with a single diaphragm pump, but there's not so many of those, so that's why we chose this one. You see the pressure, the undampened curve. There's a rise, and then it kind of is fairly flat, and then a fall, and then a rise again. That's when the pump, the piston shifts in the pump. If you compare that with the well, we'll look at some other pumps as well. It's fairly it's smoother than some and not as smooth as others, right? The blue line is with a dampener in place. All right, we'll look at, often people forget to dampen the inlet side. This is a graph of the inlet side. It's really quite radical. This actually is on the same pump that the previous graph was done on. That's the output side. This is the inlet side, and there's the dampened curve with the inlet stabilizer, and this is with the without. Right, and we'll go to a metering pump. You can see it's a very different graph. This is a single piston metering pump. You can see there's a sharp rise and then a fall where there's nothing basically. That's where the pump is filling, and then it gives another pulse. So it's a fairly rough curve, needs a larger dampener, obviously, right? Because it has to fill in more fluid. All right, we'll look at another one. This is a peristaltic pump, a hose pump. It's a very radical curve, and then there's the dampened line there. I don't have a graph from a single shoe pump. It's basically just remove this one, so you have a much longer time between pulses. So again, in that case, it needs a bigger dampener. All right, so those are the curves. And so how do we calculate what the how big a dampener should be. As you can look from one graph to the other, they're quite different, so you're not going to have the same performance if you look at just the volumetric flow rate. So we develop a factor that kind of takes that into account, but let's go through a little bit of the math first. Okay, we have pulsation in the system. You know you need a dampener to get rid of the pulsation. How big should it be? There's a number of calculations. There's kind of two calculations you could use. There's the isentropic process, which is usually the one that we use. There's also the isothermal process, which means that it's a slow process and that the gas in the dampener has time to temperature to equalize with its environment. It's generally not the case with pumps. It is the case with some accumulator type applications. So I throw it in there. Sometimes it's the one to use, but we've got the resulting or the final pressure is equal to the volume, the initial volume, divided by the final volume, and with which is raised to the nth power there, which is a constant that depends on the type of gas. And then times that times the initial pressure. Now, make sure that the pressure you use is absolute pressure, not gauge pressure. You have to add atmospheric pressure back into it or the results can be quite off. And anyway, we usually just use 1.4 for the gas, which generally it's nitrogen or air at somewhat close to room temperature. If it's way off in that, you might want to use a different number. All right. Now, the units of the volume, you can actually use any unit you want because the units cancel out. So you could use metric units and you could use pressure and PSI and you'd get the right answer. That's kind of a strange thing, right? Don't want to do that too often, but it does work. Just as long as this pressure and this pressure are the same units and the volume is in the same units. Through the ideal gas law in there, that's you can use that too if you have temperature information, which generally is not available, but sometimes it is. So, okay, continue on here. Obviously, we've got to make assumptions. What are valid assumptions? We can assume a fairly steady flow rate in the piping system. If that is not true, then the formula won't give you the actual results. And then, of course, there's continuously varying flow rate from the pump. Like I said, it's better to use the isentropic formula in most cases. That kind of gives you the worst case, which is generally what we like to design for because there's often factors that we don't know that come in there, and so better to have it a little bit more dampened in theory. And if it's too dampened, usually you're okay. That can be a problem also if you get too large a dampener, especially if it's like a metering application. You may get varying flow rates, which you don't want either. So the right size is good, and also too big is extra money and expense and all that. So we don't want to go there. Okay, add a couple of variables here to the calculation. If we have a dampener, it's not totally full of gas or fluid. If it is, it isn't correctly charged. So we want to figure out how much of the volume of the dampener is gas and how much is liquid. So we have the variable here, VPR, which is a % gas fill. So generally, we like to have the dampener, we figure about 80% gas and 20% liquid. You can go down to 90% gas and 10% liquid. That's fine. Don't want to go less than that. Because if the bladder hits the bottom of the dampener, then you'll get an instant stop in flow, which is what we're trying to get rid of. Okay, we have the volume 1 is equal to the volume of the dampener, VD, times the percent of gas fill, right? So simple calculation. All right. So we got a volume of the pulse. So that's a very important piece of information. A lot of times that you have to do a little bit of calculating to find out what that is. Most pumps don't give or pump manufacturers don't give you a volume per pulse. They will give you a volumetric flow at so many RPMs, and you can back into it from there. The volume 2 is equal to volume 1 minus the volume of the pulse. So the volume of the pulse goes into the dampener, and for the moment we will just assume there's no flow going out there because it's very hard to do the calculation otherwise. So now, okay, we will look at, we come up with a factor to account for the fact that there's flow going out and the flow coming in is at this varying rate. And we do that by experiment. And this is the formula that we use for that. It's basically the isentropic formula. We just add the factor in for the VP. And this is what we get. This factor, volumetric flow, pump correction factor, VD, is equal to the initial volume times 1 minus P1 over PA. And PA is the measured maximum pressure in the system. So we would go back, well, let me go back here. So the PA would be that point right there, which is the maximum pressure that I'm seeing in the system, and the P1 would be the minus the lowest pressure that we have in the system there. Go back to where I was there. All right. And then that's 1 over N, which is our gas constant again, and our VP, which is the pulse volume. So it's a little nasty looking equation, but it's not too bad. Put it in an Excel spreadsheet, you got it once, and then you can calculate as many times you want. Okay, now we can rearrange the formula again to give us a volume of the dampener that would be required for a given change in pressure. We can use this factor that we've developed from experiment, put it in the formula, and we put our desired pressure that we're looking for as a system performance, and we will, this formula will give us the volume of the dampener that we're looking for. We can rearrange the formula again, and this will give us, given a dampener, our dampener's volume, what the pressure is there. What pressure 2 will be. So there we go. Now let's look at an example here. We'll look at the hose pump that was on the previous graph there. It's a 2-shoe peristaltic 2.5 inch peristaltic hose pump with a 415 cubic inch dampener on it that is 90% filled with gas. And the base pressure of the system is 16.88 psi, and the pulse is 76.9 cubic inches. So we put that into the formula, and we get a calculated variation of 28.9 psi. And of course, we've added our 14.7 psi to get from gauge pressure to absolute pressure. And again, we subtracted it for the final result to get it in gauge pressure, because that's what we want to look at in this case. So the measured variation for this pump is actually 7.33 psi, which is a fair bit less than the 28 psi. So we put these numbers in the formula, and we get this factor of 0.673. So that's our valuable number that we're looking for. So in another 2-shoe hose pump, we can use that factor and get a pretty good approximation of what the pressure will be. Obviously, there's variations in systems, variation from one manufacturer to another, and there'll be some variation from hose from one size to another as well. If you're really if you need to have a really precise answer, or if a spike is a real problem, you probably want to oversize your dampener, maybe put that as a 0.7 or even a 0.8 just for a little bit of safety factor. Here are some, a little table that shows a few values from, for this factor for different hose or different type pumps. Single shoe, that's kind of an approximated number. Haven't actually measured that one. There's the 2-shoe one, air-operated diaphragm pump. You can see it's much better than the hose pump as far as the actual fluctuations, so the dampener doesn't need to be as big. There's Simplex single acting, which is similar to the hose pump, a little bit better. And a Triplex, okay, look, it's much better. And then you go down to a Quintuplex, and it's very flat. It doesn't need a huge dampener, but in a lot of cases, these Quintuplex pumps have real high pressure, and you want to put it on there often to get rid of the pulses. All right, let's look at some other factors to consider. Frequency response. Most of the times it's going on an air-operated diaphragm pump or a metering pump that's running at 10 hertz. It's a low frequency. The dampener has plenty of time to respond. The mass of the fluid in here is not a huge issue. This setup here is a flow-through design of a high-pressure pump. This one is, we've got 156 pulses per second going into this pump or into this dampener. In the flow-through design, my factor is 0.1, which is fairly close to the factor that we looked at here. And if we use the coming in the bottom, the standard way for that high frequency, the factor is 0.36, so it's much different. Interesting. And most of the time, most cases, the coming in from the bottom is preferable because it's so much easier to maintain. If you have an issue, you pull it out, put another one on. You don't have to disconnect any piping. And that's nice, of course. And you can turn it off, and it's a little bit easier to work with. So that generally offsets the extra benefit you get from a flow-through. If you have a system that's really noisy, the flow-through is a better design. It gets rid of kind of noise, whereas the noise kind of just goes right through. Another factor, of course, is dampener placement. We recommend that the dampener be placed within 10 pipe diameters of the pump discharge. Better if it can be just teed right off of it immediately. There again, you get frequency response and noise. It's much better if it's close, because the pump or the dampener, there's mass in this system, and if you get this further out, there's more mass in the pumping, which has to accelerate and decelerate, which makes the dampener less effective if it's far away. You actually get little water hammer spikes in that little section of piping, and it kind of goes back and forth, and it can create quite a bit of noise. So shorter distance, much better. All right, let's go look at the next thing here. Other factors, water hammer. There is, or we can also say pressure transients due to variation in fluid velocity. They happen all the time in almost every piping system. The question is whether it gets to a point where it's an issue. This is a dampener that was installed in a system and busted the bolts. There's a water hammer spike coming from somewhere way down the system. People don't often forget that water hammer travels from a source and goes away from the source, and can go all the way back to, well, in this case, it went all the way back to the pump. So the valve closure, check valves, flow separation, all this can create water hammer, which can cause issues in your piping system. So definitely a factor that needs to be taken into account when you're sizing the dampener. You can oversize the dampener to account for some of that. Or better yet, you can put a dampener at the source of the spike and take care of it there. This is an interesting picture. This is a hydroelectric plant in Russia that failed. It was mostly because of poor maintenance. There was bolts that held this thing down, but it was a water hammer spike that took it out. And as you can see, that's a man right there. Huge amount of damage from water. And here's another case there. All right, other factors. Proper gas charge. We always say this. You'll probably see this in any one of our training videos. There's some very important things that often get missed. Gas charge is one of them, and dampener placement is another for sure. If we look at this graph, this blue is the undampened pressure curve, and the red is a not enough air charge in the dampener, and this is a good air charge in the dampener. It's a huge difference in the spikes there, and the exact same dampener makes a huge difference how much air is in it. So you don't want the bladder to go all the way to the bottom. If it's overcharged, you'll still get pressure spikes. And if it's undercharged, you get pressure spikes as well. So proper charge is very important. Another factor to look at is AOD, especially in AODD pumps, is pump back pressure. This is true in metering pumps as well. If there's no back pressure, you'll still get some variation in flow. The dampener likes to have a little bit of, it works much better if there's a little bit of back pressure in the system. If there isn't any back pressure in there, we often recommend that people put a back pressure valve, just like a partially closed. There's a little flow restriction that gets a little pressure in the system. Right. If there's another thing especially with air-operated diaphragm pumps, because the valve in the pump it switches at the end of its cycle, that kind of is somewhat of a constant. It's not a total constant, but it's somewhat of a constant. So if you're running at a real high pressure, the valve will switch and just immediately start pumping, and you'll have kind of a long section of where it's flowing fairly constant. Your dampener performance will be a little bit better than calculated. And if you go at a real low pressure, it's faster, and the dampener needs to be slightly bigger. It's not a huge factor, but it's something to consider. Noise in the system, something to consider. It can give you results that seem higher than they ought to be. If you look at this, there's quite a bit of, about 20 psi about 10 psi. What is it? There's a fair bit of pressure fluctuation there. That's noise coming from, in this case, it's air-operated diaphragm pump, so there's a little ball check valve in there, and they bounce, and it creates this pressure wave that goes through the system. And sometimes that's an issue. Generally it's not, but it gives, if you have a fast-acting gauge, it will pick it up. Gauges are another source of misleading information. There's a lot of gauges, really nice, expensive gauges. They've got little tiny orifices that allow the fluid to go in and out. They're snubbed. Makes them very slow to respond. It kind of protects the gauge, which is great. But if you're trying to measure a fast changing system, it doesn't give you a good response. And so you may have one of those gauges on your system and say, oh, hey, it's working beautifully, when in fact there is really quite a bit of quickly changing pressure fluctuations. Pressure transducers are great for measuring those anything from noise to the quick variations in a constant displacement pump. As you look at here, these are all done with a pressure transducer, of course, because we recorded it. Another thing to look at too, sometimes you'll put a board-on tube gauge that has a little meter on it to telltale, so it will tell you where the highs are. We've had some cases where they've overshot quite a bit in rapidly changing situations. That's something to consider as well. Or they will undershoot also, depending on the speed of what's happening. All right, so conclusions here. I've kind of put all the variables that you need to keep track of here, and the factor formula, volume formula, and the pressure formula. Those are ones we need to remember. There again, remember the pressure is absolute and not gauge, so we get the right answer. The specific heat ratio N, it's 1.4 in most cases. If not, you can look it up in a table. So there's the calculations and our conclusions. All right, to do this correctly, you've got to collect accurate information. That's sometimes the hardest thing to get. We'll get information and we'll do all the calculations, and well, all of a sudden, well, there's something missing in the data, or it's not correct and the results don't match. Obviously, like anything, you have to have the correct information to get good answers. Do the math. The math is fairly straightforward. You can put it in an Excel sheet, as we said before, and it's not too difficult. Also, don't forget to consider the rest of the system. What's going on downstream of the pump can have way more effect on what's going on than people often think. Of course, install the dampener correctly in the right place with the right charge. And if we do that, we will enjoy smooth flow without shaking or pressure spikes. So hopefully this is useful and valuable for those of you trying to calculate what's going on in the system.